coordinate senza questo tipo di problemi. Io monito questo rapidamente.
Okay, we can start. Good morning. I'm Marco Roverati. I'm a geologist and I work at the Agency for Environment of Emilia-Romagna. The agency authorizes and carries out checks on the matrices involved in pollution in accordance with the provisions of Italian legislation. We start the 11th session about the innovative characterization technologies and digital innovation. And we present also the other chairs, water, and you can speak water, you can present you.
Good morning as well from my side. My name is Wouter Gevaerts. I'm working for Arcadis and I'm a director for contaminated land and environment in Europe. And I'm also the chair of the service provider group of Nicole. And Nicole is a network working on around contaminated land in Europe.
Okay. And so I don't know if we have Juliana. If she's not here, we can start the presentation. And so the first presentation is a real-time environmental monitoring of SARS coronavirus 2, harmful bacteria and toxics in water and wastewater systems. We can start maybe.
Marco, I think Charles is not online yet.
Okay.
Switch to the second, maybe.
Okay, so we start the second presentation, high resolution site characterization of PA contamination in Ghent, Belgium, by application of the optical image profiler. Peter Buffer, you can start your presentation. Thank you.
Yes. Is my screen shared now?
Yes.
Yes, okay, great. Thank you all for the opportunity to present our case at this interesting conference. I'm very happy to participate in this complete virtual conference. I'm really impressed about this enthusiastic organization. Let's hope the technology is on our side in the following time. So first, let me introduce myself and our company. My name is Peter Buffel. I'm a bioscience and an environmental engineer. I've had the opportunity to work in the last years for the INISA team. With INISA, we provide high-resolution site characterization services on project sites in Europe. We believe that by application of state-of-the-art technology in the field, more and better data will lead to improved understanding of problems related to soil and groundwater, which in turn will result in better risk evaluation and remediation designs. We apply different on-site detection tools to collect more information on contaminant situation and soil properties. INISA developed a unique combination of the direct push tool, the membrane interface probe with the GCMS detection to map soil and groundwater contaminants of VOCs, especially applicated for the detection of chlorinated solvents. But today's topic will be about a relatively new site characterization tool we also apply, and that is the optical image profiler. The project I will be talking about today, we have supported the environmental consultants that was Witteveen and Bos Belgium with the on-site measurement in the context of a detailed site investigation that was performed on behalf of the Public Waste Agency of Flanders, OVAM. The site we are talking about is one of the lots that is redeveloped in the city of Ghent as part of the Oude Dokken, the Old Docks project. So on behalf of OVAM, Witteveen is conducting a more detailed investigation of the contaminant situation in order to evaluate different remediation scenarios on the site. Here we can see a short shot from the site and the equipment we use to perform the OIP investigation. The site is located only 1 kilometer of the city center of Ghent, Belgium, as part of the Old Harbor. The site has known several owners and rich industrial history, different activities spanning back to more than 100 years. There has been a creosote treatment plant for railway sleepers, coal and fuel storage, repair shop, metal scrapyard. Because of this broad historical use, the site has different types of contaminations, of which the most challenging are the fuels, oils, and creosote contaminants. Because creosote is a dense non-aqueous phase liquid, a DNAPL. It's heavier than water, so it sinks into the soil well below the groundwater table. On this way down, the pathway is determined by the soil characteristics. So the difference in the grain size of the soil type will guide the dispersion of the contaminants. Finer grade material will initially act as a barrier for vertical movement and will initiate more lateral spreading of the contaminants. And over time, diffusion and advection will result in more storage of the products in those finer textural layers, from which a slow dissolution to groundwater will lead to the extent long-term groundwater plumes. This typical dispersion leads to very complex contaminant situations that might be rather difficult to apprehend. Several site investigations were already carried out at the site in the last couple of decades using the conventional soil and groundwater sampling techniques. However, limited attention had been given to the contamination at greater depths. The rather limited data density of traditional investigation methods resulted in a conceptual site model that contained significant data gaps and uncertainties, and that hindered the design of a sound remediation plan. So therefore, Witteveen and Bos proposed a high-resolution site characterization approach with the optical image profiler to increase the data density. And we performed around 44 soundings to a depth of 15 to 20 meters in a 25 meter space grid. And this fieldwork was carried out in about 2 weeks. The optical image profiler. This probe is developed by the Direct Image Group of Geoprobe in the United States. The probe has a UV light source and a camera. And the UV light source will excite PEH molecules, and they will emit, and the emitted fluorescence will be captured by the in-probe camera. The probe also has an electrical conductivity dipole to measure electrical conductivity, and that is dependent on the grain size. So also optionally, a combination probe that includes the combination with hydraulic profiling tool can be used to collect more information about permeability. The next slide contains some more information about how the fluorescence works, but the time is rather limited, so I skip this one. The absorption and emission spectra are dependent on different compounds. So smaller PEH compounds like naphthalene, which is present in gasoline and diesel, motor oil, they can be detected with the UV light source. But larger PEHs, which are present in heavier tar, maybe a little bit in creosote as well, they are less detectable with UV light source because of the quenching effect. The heavier compounds, they will absorb the emitted light of the lighter PEHs, and less signal is detectable. But Geoprobe has developed an alternative light source in the probes with the OIP green that can be used perfectly to map these tar PEHs. Important to mention, BTEX or chlorinated solvents are not detectable with OIP, but of course can be detected with the MIP. There have been reported detections of chlorinated solvents, solvent DNAPL with OIP, because sometimes chlorinated solvents can contain PEHs because of their use as degreasing solvents. So there might be some PEHs soluted in the CVOC, and in that cases, chlorinated solvent DNAPL might also be detectable with the optical image profiler. Here we see some results of the bench study GeoProbe did with different products and mapped the response. Important to notice, OIP does not respond to contaminants in solution, so it's used to identify contaminants attached to the soil and that are present as maybe residual NAPL. We see OIP response, for example, with diesel, starting from about 100 milligrams per kilogram and high intensities, and deviation of a linear response is observed from around 10,000 milligrams per kilogram. The probe is advanced into the subsurface by a direct push rig, a GeoProbe rig. It can be hammered, and during this pushing and hammering, every 1.5 centimeter, an image under this UV excitation is captured. Under good condition, as a prediction rate of about 100 log meters a day can be possible, which is much faster than we are used to do with the MIP system, of course. The captured images are analyzed with digital filters, and the results are expressed as a percentage of pixels that contain fluorescence. And during the advancing of the probe, we can see this type of logs in the field, showing the electrical conductivity, for instance, on the left graph, the gray one, and the blue indicating the depth at which we observe fluorescences. Here we see some examples of the site in Ghent. We see different fluorescent colors as well as some visible light images that give some details about the sediment. Most of the contamination was found in the top, more clay layer, down to about 8 or 9 meters below ground level. However, the product clearly appeared to have found its way down to the clay, down through the clay in the underlying layer with lower electrical conductivity. Signals indicate a more coarser, sandier material, and at several occasions, higher intensities of fluorescence have been detected around 15 and 18 meters below ground level. Please note in these vertical profiles, several peaks indicating dispersion of product in very thin layers, sometimes only even 3 or 4 images, images showed fluorescence, which means that the layers are only maybe 10 centimeters, 20 centimeters thick. So these high resolution measurements definitely give for OIP literally a better image of what's happening in the subsurface. These kind of thin layers are very difficult to map with the traditional soil sampling system. And after these OIP results, of course, some subsequent soil and groundwater sampling at identified locations have been performed in this project. The images have been compiled in visual bore logs that also can be displayed according to the fluorescent color. We observed several OIP profiles showed more yellow or green fluorescent color that were not detected with the standard image processing filter. So we developed additional image processing tools to also take this information into account and to make some more advanced profiles, as we can see here. All data were compiled into a 3D model. In this model, on top we see the OIP results in purple with different shades of depending on the fluorescence percentages, and the yellow, orange, brownish background. You can see there shows the electrical conductivity. So the darker the color, the more clay the soil. is over there. We clearly identify two source areas. And below we see also the available soil samples that are plotted in or modeled and plotted over this OIP model. And this is visualized in the green, red, yellow color plume. To the left, we see the lower purple OIP signals that were not yet discovered in the first soil and groundwater investigation. So an important part of the contaminants that was not known before. To verify these OIP signals, more soil and groundwater samples should be applied at the site. And a detailed comparison between the OIP and the soil samples enables the verification of both models and reduce uncertainty. Places where both models indicate differences, we know we need some more data to verify what's going on there. Here we see another output of the 3D model. The soil samples were mapped and visualized to try to make a compiled model of the site. And given the heterogeneous presence of the contaminants in comparison, the comparison of collated OIP logs and soil samples can be a rather difficult task because of the very heterogeneous character of this type of contamination. And we noticed even the comparison of collated soil samples which are only 1 meter apart, two or three different soil samples can yield surprisingly different results. The general conclusion at this site was that at a 10% fluorescence level,
2 minutes left.
Yeah, thank you. 10% fluorescence level in the OIP data seem to correlate more or less with the intervention values of this site. The investigation approach enabled a time and cost-efficient collection of horizontal and vertical qualitative information on the contaminant distribution. I think OIP profiles help to understand the very heterogeneous dispersion of this type of contaminants, and approaching a contaminant site from different technological angles help to cover the weaknesses that are inherent in each data type. And we need multiple lines of evidence that will get us hopefully closer to the ground truth. Yeah, thank you for your attention. I would like to thank the organization for the opportunity to bring this story. I hope it was interesting. My time frame was rather short, so I made quite a hurry. I just touched some examples to give an impression of what can be expected with this type of tools and investigations on site. Finally, I also like to thank Witte van Bol and OVAM for the good collaboration in this project. My contact details are on this last slide, so get in touch if you like more information. Thank you.
Okay, thank you very much, Peter. And I see that Charles Lee is online now. He can start his presentation, and is the real-time environmental monitoring of SARS, coronavirus 2, harmful bacteria and toxics in water and the wastewater system. And Charles, you can, okay, you can, I see you can start your presentation.
Okay, I'm trying to share my screen here. Can you see my screen here?
Yeah, yeah.
Okay, let me try again here.
Yeah, you can put
is this okay?
presentation in full screen. Okay, perfect.
Full screen, okay?
Okay.
Let me try the yeah, I think let me display the, is this good?
Yes,
Yes.
Okay,
Okay.
perfect now.
Okay, thank you so much. Yeah, apologize for me being late here. Got held up somewhat. I'm in Singapore. Thank you so much for the organizers for having me present this paper in this prestigious RemTech Europe conference. I'm at the University of Newcastle, Australia, but based in our offshore campus in Singapore. Happy to be here. My topic, as you know, is on real-time environmental monitoring of different toxics, harmful bacteria in water and wastewater systems, in particular, the latest on SARS coronavirus 2. The outline will be what is real-time 24/7 monitoring. I'll define it as one slide. And some of the technologies are not quite new. Fluorescence detection of the bacteria, viruses, toxins, using excitation emission spectroscopy, as well as the molecular probes using qPCR, and highlighting the latest wastewater epidemiological the cases to detect this coronavirus. So in terms of real-time monitoring, there are a couple of misconceptions. So the way it's defined here would be real-time 24/7. That means we are putting sensors real-time in the field, in a very complicated field environment. You know, it's very complex natural environment like weather monitoring, water quality. You put the probes in the river, in the reservoirs, wastewater treatment plants, and be able to monitor your crucial parameters, pH, for example, algae, you know, the algae blooms, microbes, bacteria, viruses. We would have real time. That means we're getting the data, even if you're sleeping, it's collecting the data so that it will provide an early warning system. So it uses IoT, the sensors are very common nowadays, and increasingly a lot are coming out in the market. Putting it on the cloud, and then be able to monitor it real time, you know, in your bedroom, in office, or someplace that you're comfortable with. So the fluorescence detection technology is not new. I'll go through very quickly. It uses excitation emission spectroscopy, which is a combination of physics and bombarding your light at different frequencies at your organisms, which is inherent. So if you look at phytoplankton, some of the pigments in the cyanobacteria, you would excite it with a wavelength of, let's say, 450, 660, and then there's a lag period. It will give emission spectra of a little bit longer wavelength. So with that, you're able to identify the pigment and the particular bacteria or virus in the water systems. The probes can give you then with algorithms real-time data, right? So that's not new. And you get the spectra, and with algorithms you get real-time monitoring data to help you identify algal blooms and different early warning systems. Moving on then, more excitingly, molecular probes. More recently, I guess from the Human Genome Project, that was the first time that the DNA sequence was identified for the human genome. And then the bacterium genome has 1.8 million base pairs. So we have this signature that we can identify the bacteria or the virus. And so using PCR, which is the polymerase chain reaction, you're duplicating, enhancing that signature of the genome. You're able to lock into specifically that particular bacteria or the virus. For example, this case, the SARS coronavirus 2, which we have the genomic sequence given by the Chinese scientists about a few weeks after it was found in the when it first occurred in China. So the PCR is a powerful molecular tool, and again, like I said, it's can identify specific toxins and genes in bacteria and viruses. Now, in terms of real time, it is not real time, it's real time in a laboratory. So we have tools in the lab that can do it quickly, but you still need the samples from the field, let's say, to be able to do it in the lab. So real time in the field, the LOT is still prototype, so they're not quite there yet, although it's moving towards that area very quickly. So moving to our topic of interest is how do we use these tools to help us to monitor the SARS coronavirus 2. We know it's a lot of human testing, right, of your swabs in your nasal cavities and all that. So this one is new, but not yet not so new in environmental monitoring for wastewater. It's called wastewater epidemiology. Basically, we are taking the wastewater and looking at signatures, because the wastewater is from domestic wastewater, so it tracks back to humans for us from our poop, our stools that we excrete, and it's in the wastewater even though it's very dilute. So in decades ago, you could detect polio in the wastewater. So upstream in communities, in countries that still have polio, we can have an early warning system. Opioid, which is the drugs for pain management, the abuse and overuse in many communities in the United States, in Australia, I'm sure also in Europe. We have used this detection of opioid, the drugs that we identify in the wastewater, to look at how the communities are using this drug. So you go back upstream and be able to detect it. So for SARS coronavirus 2, which I will code this as SCV2, the viral fragments, small amounts, are found in the stool. And so in the sewage systems, we can detect it by the PCR method, as we mentioned earlier, which is same for your human samples. So we could correlate very early the arrival of COVID-19 in different communities, right? As we see in Netherlands, in many communities, in many states and countries. So for example, in Boston, significant amounts of viral material, the SARS coronavirus 2, was found in sewage weeks before cases arrived in March. Because by the time you get tested, the community, and there's also asymptomatic occurrence of COVID-19, as you know, by the time you get them to test, it's a bit late, and so it's appearing in the wastewater that you can detect. So it's an early warning system that you can either lock down the community if possible, or start having healthcare systems ready for a second wave, a third wave in a particular community, right? So as said by this Bot Science US company, is every person in the toilet has a voice. So they are, as I speak, is not new now in many countries. Its results are found, and BioBot Analytics from the US and MIT startup has had looking at 400 over wastewater treatment plants testing for this coronavirus in order to help us get a signature and get an early warning system. Of course, it's not, the data is still coming in, and scientists are continuing to fine tune and get reproducible results that they can roll out as an early COVID-19 alert system. So it's a huge potential to predict COVID-19 infections in communities way before actual clinical detection, especially good for second and third wave or fourth waves, as we see happening now. So in environment monitoring is quite an exciting area, for lack of a better way to say it. Applications in Singapore, of course, is not new. We've been tracking the wastewater treatment plant. As you have read in the papers, in Singapore, everything appears to be under control. There's the least amount of death in the world, but we have a lot of foreign workers. We have about 1 million foreign workers in dormitories, and the outbreak just was catastrophic in the dormitories. So the detection was put in the manholes next to the dormitories, for 20 dormitories, to try to prototype, test out this method of using wastewater monitoring of SCV2 in order to have an early warning system. So this enhances and adds on to the clinical testing. Also gives a good warning system for clearing the dormitories, the workers to be able to go out to work, or lock down the dormitories. Each dormitory could have a few thousand workers, some as many as 10,000 workers. So we're using this as a tool to help us to have an early warning system for lockdown versus semi-lockdown of the dormitory. So it has been going on for a while. As I said, early warning system, the viral material is detected in swabs and in very early cases, and we could isolate the dormitories. The manholes, as you see a picture here, we have the ISCO automatic samplers, although the sample is still taken manually back to the laboratory for analysis of the SCV2. So it's very labor intensive. That's the best we can do for now. The labs can process it very quickly within 24 hours, but you still need the sampling to be done semi-automatically. So what is being proposed here is also not rocket science. It would be down the road, basically the sensors right now is still in a PCR in the lab. Common is a small, tools available, but it's still not quite automated. So we're looking at the PCR to identify SCV2 on a chip, lab on a chip, which is a lot of prototypes available. Hopefully for this SCV2 that's been developed, put on a chip, so it becomes an IoT tool. We install it in the clusters of manholes, put in specific wastewater treatment plants, and of course put it on a network, right? A scalable network would be like a LoRaWAN network server, very inexpensive, and put an IBM cloud, process, store the data. You could then identify, measure, detect the SCV2 in the system, like in the manholes. Then you could look at the data to help you quite readily.
Sorry, Charles, yeah. 2 minutes left.
Okay, and give you early alert systems. You set thresholds. When you first find it, it will give you early alerts to go to the dorms to swap the workers or shut it down. And that's the whole idea. So it probably will be quite a ways down the road, but I think once the lab on a chip is developed, we can then put it on a system that is not new in terms of putting monitoring systems on the cloud that we can detect. Yeah. So that's kind of where we are headed, and I hope it's been useful. Thank you. I have a collaboration with Joop Appels from Microline Netherlands. We've been doing a lot of this real-time monitoring, as well as working with the wastewater treatment plants in Netherlands on COVID-19, on this coronavirus SARS-2. And if you have any questions, please write to me. I also apologize I won't be around for the Q&A. I have a class to teach, but I'm looking for any collaborations and happy to work with any of you on this area, in this area. Thank you very much for having me present, and all the best, and enjoy the rest of the conference. Thank you very much.
Thank you, Charles. Thank you really much, Charles. And I saw Chiara in online. And,
yes.
Yeah, okay. The title is Characterization and Analysis of Groundwater Recharge through Tritium and Tritium Measurement.
Okay, can you see my screen?
Okay, yes.
Okay, thank you very much. I am Chiara Telloli from the ENEA Research Center in Bologna, and today I talked about a new methodology to date groundwater. So before starting, a short introduction on the importance of water in our life. First of all, the key to good water management is knowledge. How much water we have, where it comes from, where it flows, what age. because young water is easier to exploit it and old water is more precious and needs to be protected. But young water is even more vulnerable. And this is a problem because the vulnerability of young water prevents the formation of old water. The study of water and its presence on the surface and in the subsoil is carried out through the hydrology that studies the distribution and movements of groundwater and the influence that the geological environment has on their accumulation and circulation. Water, through circulation and charging, transport isotopes around us. And for this reason, hydrology uses stable and radioactive isotopes in water to trace its processes. But what are isotopes? Isotopes are atoms of the same elements with different number of neutrons, and they are divided in stable and radioactive. Stable, for example, deuterium or carbon-13, they are characterized by fractionations, and they are used as tracers, for example, to trace the origin or the genesis of the aquifers. On the other side, radioactive are, for example, tritium or carbon-14, and they are characterized by a radioactive decay, and they are used as clock, for example, in this case, to date hydrological processes. Each isotope is characterized by a specific decay, in which, after a specific period of time, the mass of the isotope became the alpha, until it decays into another more stable element. This is an example of the use of the isotopes as clock, because each isotope is characterized by a specific decay time. For example, tritium decays in a period of time of 12 years. Or another example is carbon-14 that decays in a longer period as 5,740 years. So each different isotope has a different time of decay. Tritium is an unstable isotope of the hydrogen element. The hydrogen has 1 proton, deuterium 1 proton and 1 neutron, and tritium 1 proton and 2 neutron. For this reason, tritium is the heavier isotope of hydrogen element. And with by emission of beta particles decay into anilio atoms. It has an element mainly of cosmogenic origin. It is generated in the atmosphere by the interaction between cosmogenic ray and nitrogen-14, or with interaction by deuterium present in the stratosphere and upper troposphere. But another example of origin of tritium is anthropogenic. For example, from nuclear tests, especially from 1952 to 1963, and from nuclear power plants. These events, especially nuclear tests, change the geochemical footprint of the rainfall, with significant increases in the atmosphere of the radioisotopes. Fortunately, these events were stopped with the international agreement of CTBT, that is the Comprehensive Nuclear Test Ban Treaty, that banned all nuclear tests. Tritium in atmosphere produced by natural or anthropogenic origin, combined with the oxygen present in the air, produced tritiated water. The tritiated water has a greater molecular mass than water molecule, because, if you remember, tritium is heavier than hydrogen or deuterium. This means a short residence time in atmosphere because of precipitation. So, the amount of tritium in surface and groundwater depends on two principles. On the amount of tritium in the atmosphere when precipitation is formed, and on the time it takes for the water to go from the surface to the groundwater. And this is important because short periods of residence in the atmosphere and short period of decay, and I remember you that the period of decay of tritium is 12 years, gives tritium concentration in rains that becomes constant and very low. Another important information is that the decay of tritium, for example, in groundwater, so without absence, without recharge, for example, for rainwater or precipitation, so the decay of tritium produces its continuous loss, and this causes a decrease. And this means that we can have fossil water or old groundwater that is very precious. Before we talked about nuclear tests. Nuclear tests have generated in the atmosphere high concentration of radioisotopes and tritium-2. And after the stop of the nuclear test, the concentration of the radioisotope in the atmosphere began to decline. So we can divide in this slide into three parts. The pre-nuclear test, in which the concentration of tritium of natural origin in precipitation is almost constant. During the nuclear test, in which tritium concentration in precipitation increased 1,000 times, especially in the northern hemisphere. And the last part of this slide, in Science 1963, the volume of tritium in precipitation has decreased. This is more important because due to the very short time of decay of tritium, the groundwater infiltrated before 1950 does not contain tritium. The other, so after the water infiltrated after this time, they are called young groundwater, and they have a time of period less than 100 years. Analyzing tritium in groundwater is more important because it is possible to trace the age of the aquifer and or define if the aquifer is polluted by anthropogenic activities. Yes, because we live in the modern era and we are subject to anthropogenic pollution, and so I can have old water, but in old groundwater, I can find tritium to anthropogenic activities. The analysis of tritium requires a good capacity, especially if I have tritium water in concentration below the detection limit. And this is possible only through an enrichment procedure and analysis with low-level liquid scintillation spectrometer. The ENEA's Environmental Traceability and Radiometry Laboratory is part of the Fusion and Technology for Nuclear Safety and Security Department, and is part of Nuclear Safety and Sustainability Division in Bologna. The laboratory is also part of the High Technology Network in the Emilia-Romagna region, and this is our website. And we have two different kinds of research centers, one in the Brasimone, that is located in the Apennine mountain, and one in the Bologna city. Especially the Radiometry Laboratory of the Brasimone Research Center is at the forefront of the analysis of radioisotopes in the environment, including low concentration of tritium analysis. This is an example, a photo of our distillation systems, in which we need at least a liter of tritiated water. And this is the second part, a photo of our enrichment system with electrolysis system. So the sample obtained after distillation and enrichment are mixed with scintillation liquid in Teflon vials and analyzed in Quantulus. Quantulus is a low background instrument that allows to carry out analysis of sample with very low concentration of radionuclide and tritium-2. This is an example of tritium spectrum that we obtained by the instrument of Quantulus. We have the amplitude of the electrical pulse that is converted in digital value of each channel that is represented in the X-ray, and the channel represents the energy. The energy range from 0 to 2000 Kelvin. Our case study that I want to show you is the case study in Treviso in collaboration with the Department of Physics and the Sciences of Ferrari Universities and ARPAC of Treviso on the determination and evaluation of the concentration of tritium in groundwater samples collected in the south side of Treviso that you can see in the map on the right. Before to give you the result, I want to explain the classification of Clarks and Fitts on 1997, in which, knowing the activity of tritium, it is possible to take the water sample. For example, if the sample not have tritium, it means research times more than 70 years. Or if the sample has a tritium activity between 0.8 tritium unit and 7 tritium unit, the age estimated is between 1 and 70 years. Or at the end, if tritium activity in the sample is major than 7 or major than 15, means a possible or an evidence presence of external contributions. External contributions, so anthropogenic contribution, for example, leach from landfill hosting photoluminescent objects, or from another example from hospital wastewater, or from biological laboratories. So I can have a lot of different kinds of anthropogenic pollution. And this is our result. As you can see, a lot of samples represent a long research time, or 15 or more than 60 years. The small samples colored in light blue or green, the very, very small samples. The pink-orange sample represent water with age estimated between 10 and 50 years, so a very young water with a young research. But the most important are the pink samples and the blue one, especially the pink sample, because the pink sample represent the possible presence of external contribution. And these samples are unexpected from ARPA and for us. So in this case study, tritium is more important because the sample, thanks to tritium analysis, show typical value in accordance with the young age of water recharge. And this could be possible through the contribution of surface water and through differences recharge due to change in permeability of the sediments. This means that Treviso aquifer is also very vulnerable. So isotopes are most important to dating, to understand the genesis, the recharge speed, and the vulnerability of an aquifer. And that the study of tritium concentration in groundwater is a very useful tool for the determination of reagent exchanges with surface water, or, more important, the presence of reagent anthropogenic contributions.
Sorry, so, 2 minutes left. How about you? You are maybe finished.
Thank you very much. I finished my presentations.
If you can speak 1 minute, you have time, Chiara.
Yes, I want to give you this presentation because the measurement of tritium is not always a standard methodology because not a lot of laboratories give this analysis, but it's more important to give you a lot of information, not only in the age, because in general radioisotopes, they are used to date in archaeological samples. But it's important not only to dating, but to found anthropogenic pollution, especially in groundwater. And so it could be a very useful tool. So if you have a question, I can respond to you in the chat.
Okay, thank you very much.
Thank you.
For your presentation. And now we don't have Simon Levy, but we have a short presentation of the title Environmental Release Simulation and Testing to Inform Hazard Assessment and Risk Mitigation. And we can start, okay, the presentation now.
Just tell me, Marco, if in the first 10 seconds, if everything is working.
Hello, it's truly my pleasure to be with you today at RemTech Europe. My name is Simone Levy. I'm a research scientist with InnoTech Alberta Environmental Services Division, and today I'll be presenting on environmental simulation to inform hazard assessment and risk mitigation. The outline for my presentation, I'll talk a little bit about InnoTech as a semi-governmental research and technology organization. We're a wholly owned subsidiary of the Provincial Innovation Agency, Alberta Innovates, and what we do is applied research and innovation. I'll talk a little bit about InnoTech, about Alberta's risk-based guidelines, which help to frame up some of the work that we do, simulation and testing programs, and then some and the strategy that we use, and then some examples classified into land, water, and air projects. So just a little bit about InnoTech. We focus on technology research, development and deployment, de-risking and pilot demonstration facilities, analytical testing and monitoring, which I'll be speaking about, and innovation and emerging technologies. And we have MSc and PhD staff, specialized equipment, unique facilities, and about 1 million square feet of research space. And some of the work that we do is to help de-risk technologies and approaches, and also act as a neutral third party in the work that we do for government and industry. The Environmental Services Division, and within the Environmental Impact and Risk Evaluation Group, we focus on contaminant behavior in the environment, and we really work at several different scales, from microcosm or microscale, including anaerobic and aerobic microcosms, bench scale tests, above and below ground mesocosms. So we have some aquatic mesocosms that are shown here. We have 16 above ground, either terrestrial or they can also hold liquids. They have these external tanks for simulating groundwater conditions as well. So there's some of the kind of specialized facilities that we have. We have water resource investigations and impact assessments using isotopic tracers. And we also work at, on behalf of industry and government, working on regulatory approaches and provide support for, I guess, different portions of regulations for various industries throughout the province. So next, I'll talk a little bit about Alberta's risk-based guidelines, because they help to frame up our simulation and testing approach. So Alberta's risk-based guidelines are parameter specific. They have 5 different land uses. We have industrial, natural area, agricultural, residential, and commercial. And within each of those are different stringencies for the guidelines for each parameter. And there are also different receptors that are identified, either sort of primary or secondary within those. And understanding the potential land uses that we're dealing with in these environmental simulation and testing projects is very helpful, as well as the potential receptors within those. So that's sort of the starting point for some of this assessment. So I'll go through our experimental design process beyond those land uses. So I guess the first thing is actually characterizing the product, understanding its physical and chemical characteristics, thinking about release scenarios and what that looks like, or either release or environmental management scenarios. And we work on those with clients and collaborators. And that has been really part of the key to successfully running these projects, is really understanding what the conditions are in those either release scenarios or environmental management, and the challenges that are associated in the actual specific characteristics of those scenarios, I guess. So working with folks that really know the ins and outs to be able to define those, so that we can do simulation and testing that are really reflective of environmental conditions. Looking at potential land use and the receptors, experimental scale, again, that micro to field scale, we're targeting what makes the most sense. Sometimes it's multiple. Designing and conducting experiments and the testing program, analyzing results, identifying hazard mitigation opportunities, and then also identifying gaps if there's any follow-up required. So you get a little bit of an overview of Alberta and what we deal with for our challenges, at least in this environmental space. So energy is a big industry in Alberta, for those of you that aren't super familiar. So lots of oil and gas development, production, and there has been for quite a number of decades. One of the things that we're challenged with right now is the upstream extraction location. So these well sites and associated facilities and processing facilities from oil and gas production are reaching the end of their lives, and some of them have some issues that need to be dealt with. Some of the work we do goes to support that work. And then there's also the oil sands development. So in some cases, this is large scale reclamation that's being done, and we want to ensure geotechnical stability. We want to ensure that water flows through material and that it is matching the surrounding landscape. It's actually a very successful reclamation project that's demonstrated here in this photo, with some lovely bison as well. So let's get into some examples of the projects, the environmental simulation and testing projects that we do. So land first, these are some soil columns, and what we have is soils with different concentrations of salt, and we're looking at roots of some specific targeted vegetation to see how the roots actually, if they're able to, if they avoid soil with high salt concentrations. So it's going to inform remediation risk management strategy. Another part of the project, another project example is this one here. So this is more tied to the photo with the bison and looking at some hydrophobic soils. And when we put those back, if they're able to transmit water. So some of the testing that we did on these materials is understanding, in this case, how they take on and also how they release water, what kind of holding capacity they have at the day, and then also this hydraulic conductivity measurement. The complementary part of the study was actually using a pretty sophisticated piece of equipment that we have, which is an industrial computed tomography or CT scanner. So this is like a scanner that you would use if you have a medical exam, but we use it for industrial applications. And in this case, what we're doing is looking to see if dry tailings, in this case, could be layered with a slurry, and if the moisture from the slurry would eventually end up redistributing itself evenly throughout the dry tails. And so this CT scanner. This can be hard to assess, even just freezing and cutting a sample open, or another type of approach. But this is just an image, but we can also do 3D manipulation and do different slices and so on. So it was a very interesting way to be able to investigate what was happening within these columns. Another example of the CT here. So we had a simulated release to land. Wanted to know with this release of product and a synthetic precipitation event on top, if we would end up seeing a lot of leaching of some components from that product into the sand. And so we did the CT scan. This is before any product is added, after the product, and then after 7 days and the precipitation event. And then also took some samples to follow up and to sort of validate what we saw in the CT scan. Moving on to air. So this is looking at, there's a model for looking at what kind of volatile concentration you might find within a trench, depending on residual parameters in the soil surrounding that trench. Some of the work that we did, if you just keep an eye on this rectangle, go to the next slide, and show you the setup that we used. So this is a bit of a unique setup. It took some work to come up with. It looks quite simple when I'm looking at the picture, but actually it required a lot of thought, because we didn't want to lose any volatiles. We wanted to have them accumulate within the headspace above some spiked soil, but we didn't want to have a pressure issue related to the headspace around the sample. So we didn't want a lot of volatiles to come out, max out the pressure, and then that would artificially lower the concentration of volatiles in the headspace. So in this case, the approach that we took was using a glass petri dish, packed the spiked soil to known concentration of this product into the dish, placed the lid on top, evacuated the Tedlar bag. The Tedlar bag has 2 ports, evacuated it, and then added a known volume of headspace that would not max out the Tedlar bag, and then place this clip here so that we could put the sample inside. And what that meant was that we knew what the headspace volume was, but also the Tedlar bag, because it would be able to inflate, deflate according to atmospheric pressure. We weren't worried about maxing out volatiles due to pressure in the headspace. And then used a PID detector in a 4th bag as a kind of a surrogate here to be testing the flux rate and when we reached a steady state, and that's when we took a sample for GC analysis of the headspace here. And in this same experiment, this was actually some prep that was done for some of the methods, but I thought it was interesting because this is a GC scan of the distillate. So we created a distillate out of hydrocarbon products. So it was a defined range of carbon molecules and, carbon compounds. And so this is the distillate itself. And then this is what came off as vapor. So a little bit of a different distribution. This is important to understand what we might be encountering in the headspace and to plan for that. We can do incubations at different temperatures. So we've done several different incubations. We've also used different ratios of volume to liquid. And so this is this manual piston method. It's a modified ASTM D236 that is a 4-to-1. So that would be able to simulate something like a a real car or a tanker truck, where you'd have more product to headspace. And then we have another type of headspace analysis that we do on a small vial, and this is a 1-to-1. And so that really shows you kind of what the maximum would be. Sometimes we stage these analyses to understand the worst case and a more realistic case. Some things that we can do. Now there's some client sensitivity around this project, so I'm not showing actual testing photos, but we do some testing around different hydrocarbon release to water, fate and behavior, both chemical and physical. And we have collaborated with, they're actually just up the road from us, it's an NRCan federal research facility, CanMet Energy, and they have this fantastic wave tank that they're able to do quite sophisticated fate and behavior testing of different hydrocarbon products. And so we've worked with them on one project in particular that, using this specialized piece of equipment, we were able to get the answer that we needed for our client. Into water now, so some soil leaching columns. These aren't overly unique, but I guess something to mention is we've found that filling from the bottom is much more effective. You don't get the airlock that is sometimes encountered if you're trying to introduce a liquid from the top. So that is something that we do. We do these fairly regularly. Sometimes the outputs are used in modeling or different applications to understand sequential leaching events and how that may influence the various chemical parameters within the sample. And some of the work that we also do is at field scale. So related to the oil sands development with that photo of the bison, one of the things that we do is oil sands process water characterization. So some fairly unique testing that we do for that OSPW, and tying that into a conceptual model. And in this case, there's actually some microcosm studies that were done to inform some of the sort of zone effect and what might be happening, in really a conceptual site encompassing, surface all the way down to, quite deep within the groundwater. So in conclusion, we often get industry consultants, government coming to us with various environmental challenges. It's always interesting to think about how to best answer their questions. Our experimental design process, just to recap, has generally been looking at the product, understanding that product itself, looking at those release scenarios, potential receptors, what kind of tests we need to run, what kind of design we need to have at what scale. And like I said, sometimes it can be multiple or to answer the same question and tie them together, sometimes with a numerical model, otherwise a conceptual site model. Doing the testing and experiments, looking at the results, doing some gap analysis, following up. And I guess I just want to highlight, harnessing the semi-governmental capabilities. We're able to support effective risk management and support technology development in this area. So by all means, if anybody has any questions, apologies I'm not able to participate in the panel, but would very much look forward to any questions and discussion. So my contact information is here, and thank you very much.
Okay, and now we can start the last presentation. I saw Zach is online. And the presentation is about Magnet multi-scale adaptive global network for water, a cloud-powered, big data enabled, real-time interactive platform for groundwater flow and contaminant transport, modeling, visualization, and analysis.
Okay, thank you. Can you hear me and see my screen?
Yeah.
Okay, let me go into slideshow mode and then we'll get started. Okay, thank you for the opportunity to present today. I've really appreciated the sessions so far. They've been really great. My name is Zachary Curtis. I'm a water resource engineer and I'm the Chief Operating Officer of Hydrosimulatics Inc., which is a small business spinoff from Michigan State University. And today I'm going to be talking a little bit about the technology that our team has been developing over the past 2 years or so, which is really a powerful technology for groundwater flow modeling, contaminant transport modeling, and site characterization, namely the visualization of the subsurface, which is invisible and hard to characterize. So I'll first start with some illustrative graphics to give you a sense of some of the unique capabilities of the technology that we call Magnet. And then I will give a live site demonstration for a couple of minutes at the end. So let's first start with the unique capabilities. So Magnet for water is a cloud-based modeling, visualization, and analysis technology, meaning you can access the technology through a web browser on your laptop, your desktop, smartphone, or even a tablet. And so you access the model, the data, the visualization and analysis tools through a web portal. And so that all of the data is available on the web, all of the models are built and sent back to you over the web. And so truly it's accessible anywhere and at any time. There's no software requirements, there's no operating system requirements, no hardware requirements other than access to a web browser. It's data enabled, meaning there are pre-processed big data sets live linked to the simulation platform. And so we have a wing of or a branch of our company that processes global spatial data sets. So we're talking about digital elevation models for the land surface, or soils or permeabilities of the subsurface, global rivers, lakes, and wetlands, and trying to process them once and for all, and then live link those to the simulation platform so that users can basically bypass the step of pre-processing their data and immediately apply the seamless universal data sets that we now have available to us. And so here, this graphic is just showing an example of some of the data sets that have already been assimilated or are being assimilated into our database. It's a real-time interactive technology, and what that means is that as you build the model and you simulate the model, the results are returned to you in real time. And so you can visualize the outputs in terms of groundwater flow, in terms of plume transport in the subsurface, in terms of source water tracking in the subsurface, and also some analytical results, some charts like concentration breakthrough charts, or a cross section of the subsurface. And so you can see here, this is just an animation of a site in northern Michigan, which I'll demo in a little bit. And these are some of the real-time results that are returned to the user as they're developing the model. And so at any point, they can pause the model, they can change the conceptual representation, they can add data, they can resubmit the model, and then visualize on the fly what's going on with their model and what the results look like. So it's a very intuitive and conceptualization heavy process where you're iteratively improving your model and visualizing on the fly. It allows hierarchical modeling. And so this is multi-scale modeling of groundwater flow systems. And so we're often concerned with a contamination at a particular site, but we know that groundwater is a larger system and that the larger regional groundwater conditions affect the local conditions. And so we need to have some understanding of what's going on around our site and at different scales. And so Magnet allows you to easily create models at different levels and allow those models to communicate with each other. And so you can take information about the flow from one scale and use that to inform the model at a different scale. And so the idea is to solve large, complex problems as a series of smaller connected problems. It's more computationally efficient, and it's easier for the human mind to take in information at different scales rather than trying to simulate one large, complex problem. The technology Magnet offers multi-realization Monte Carlo simulation, and that is simply running the model for different types of representations of the subsurface. And so the subsurface is inherently heterogeneous and complex, and so we can never fully characterize the subsurface no matter how much data we collect. But if we can use a model to represent some likely scenarios and then run statistics on the different types of model results that you get, we can make decisions within a probabilistic risk-based framework. And so this is really useful when you're addressing a site that needs to be remediated and trying to figure out where do we place our monitoring wells, where do we place our extraction wells in order to clean up the site effectively. This type of simulation allows you to account for the uncertainty that we deal with the subsurface within some sort of mathematical or statistical framework. The technology allows you to represent the subsurface using a stochastic or random modeling approach. And so the idea is that we can prescribe some level of random variability that the subsurface may exhibit, and we can look at the impacts of that variability on plume transport. And so on the left, you're looking at a single scale model with different levels of variability or variance of your hydraulic conductivity. And so you can see the same starting plume has a much different fate or evolution based on the level of variability in the subsurface. And so as you're investigating a site, you can easily use the technology to look at the impacts of different levels of variability and try to get some sort of sense of what might be going on. And we also can look across different scales. So on the right side, we're representing heterogeneity with different scales. So we have interacting scales in the middle and lower column that make the dispersion of the plume much greater than a single scale of variability that's shown in the top row. And so these are really important. We know the randomness of the subsurface is very important for plume transport. And so this tool allows you to very easily probe and test and experiment different representations and look at the impacts that might have. When we talk about plume capture using extraction wells or extraction trenches, we can evaluate the remediation performance under different degrees of complexity. And so on the right, we have a homogeneous aquifer, and we see that the extraction and the cleanup is performing at a high level. On the left, we have a complex aquifer system, which might represent reality in some places. And you can see that the cleanup is much less effective when we're dealing with this heterogeneity. So again, the ability to model the complexity of the subsurface and to evaluate on the fly is really one powerful aspect of this technology. And to just reiterate, this really allows for real-time hypothesis testing. And so as I mentioned before, we know that the complexity of the subsurface is really important in terms of what happens with our contaminants that are moving. But we can never really collect enough data to truly characterize the reality. So we can use a model to look at different possible representations and look at what the implications are though for those different representations of reality. And so on the left, we're just looking at a cross-section model from a landfill. And on the right, we're looking at the regional circulation of groundwater flow. And so when I press play, you're looking at the groundwater flow paths. And for a system that might look the same from the surface, again, this is a cross-section in the subsurface of the Earth, you have quite different flow paths depending on the geology underneath the surface. And so in this second row, we have a high permeability aquifer underlaying our top aquifer, and we see that really changes the flow patterns compared to the case where you don't have a multi-layer aquifer system. And so this is really important in terms of waste disposal. Where do we place our landfills? Where do we place our waste disposal facilities? And what are the ramifications of that? Are there downstream ecosystems that could potentially be harmed? Are there downstream drinking water wells? And so this is really useful for understanding the system and trying to make sense of the subsurface when we're limited with data. And then sometimes if we're not, actually we usually start with characterizing the site in terms of geology before we even model flow and transport. And so one of the capabilities of the platform is to take lithologic profiles, so soil profiles and geologic material profiles from boreholes, from water wells, and we use those boreholes as input into a sophisticated geostatistical approach that allows us to build a 3D map of the subsurface. And so we can actually map out in 3 dimensions where we have materials that are typically found in aquifers or confining materials like clays or silts. And so this is really effective for mapping out where we can develop groundwater as a resource and where we may have some vulnerabilities to contamination. So those are some of the unique capabilities, but I want to just show a quick site demonstration of what this looks like and how you actually get into the platform and use some of these capabilities. And so I did a screen capture yesterday of a site demonstration, and so I'm going to play that and I'll narrate while we're looking at it. So this is the Magnet for Water modeling environment. Kind of looks like a Google Earth or Bing Maps environment. And so you simply zoom to your area of interest. So this is an area in northern Michigan in the United States. And this is actually where we have one of the largest TCE plumes in the country, and the largest TCE plume in Michigan, underneath the small town of Mansalona. And so I zoomed into the area. I drew a red box, which is my model domain. And now you can see I'm adding a source of contamination. And so this is going to be a surface source infiltrating with some amount of recharge and some prescribed concentration. This is just hypothetical. And so I've added a source of contamination. Now I'm going to add a monitoring well just downstream of that source of contamination so we can track the concentration over time. And so this is a point-and-click GUI-based modeling environment. And here is where I can assign my aquifer attributes. And I can use some of the pre-processed big data sets that I mentioned before. And so I can use that to parameterize the top elevation of the aquifer, the thickness of the aquifer, the variability of the hydraulic conductivity or the permeability of the subsurface. And then I can also assign some simulation settings. So things related to the grid that I'm using to model the subsurface. So here I'm subdividing the subsurface into multiple layers. Here I'm entering my credentials. It's free to use Magnet, free to sign up. You do have to use a username so that we can help keep track of your models. And so here I'm assigning some grid settings, and now I'm getting very close to simulating the model. And so we offer a complete set of default inputs, and you can use those default inputs to almost immediately draw a box and simulate 2D groundwater flow. In this case, I want to show you 3D groundwater flow with some plume transport. So I'm entering some additional inputs, but this is not necessary to get started. I'm all set, just double checking my inputs. And now you just click simulate, and this submits the model for simulation. And so what's going on is you've drawn the model, you've added your conceptual features, you've added some inputs, and now you're sending the request to simulate across the internet. And so you can watch the status bar at the top of the modeling environment, and that'll tell you what's going on. Right now we're connecting to the hydrosimulatic server, and we're extracting the big data sets, those pre-processed data sets for elevation, hydraulic conductivity, etc. And now this is a 5 computational layer model with 100 grid cells in the horizontal direction. So this will take about a minute to finish simulating and send back the results. Usually if you use just the default settings and you click simulate to do a 2D model, it'll be back to you with results in about 20 to 30 seconds. Obviously, if you make a larger model with more grid and more resolution of the results, it's going to take a little longer to return the results. But now the results are passed back to you on the client side, and you can see now the head contours and the velocity vectors, as well as the source of contamination, which is that colored square there in the middle. So I'm just adjusting some display settings to make it a little easier for you guys to see, just cleaning up the vectors that represent the groundwater flow velocity. So that'll refresh in just a second. And you see some purple areas. That is where groundwater is seeping to the surface. And so we predict that as part of the solution process. You can more clearly see the velocity vectors now that I've cleaned it up. I just drew a cross section through the subsurface. And now when I hit the analysis button, it's going to show me the results for that cross section. And it will also show a few other charts that are made on the fly automatically. So you have your concentration breakthrough curve at the monitoring well just downstream of the plume. You have a cross section showing the plume entering from the surface into the aquifer system, so moving along with the groundwater flow, mostly in the horizontal direction. And so you can customize, you can add your own data, or you can use the pre-processed data to get started. And you can do a number of different types of applications using the different capabilities. I think I just hit 15 minutes, so let me stop there. Thank you very much. I have one more quick slide just to give you information to actually use the platform, it's magnetforwater.com or magnetforwater.net. And this is what the website looks like. You can access the modeling platform through this link. You can sign up for a free account here. And this is my email, zach@magnetforwater.com. So feel free to email me if you have any questions or would like to collaborate in some way. Thank you very much.
Okay. Thank you very much, Zach, for your presentation. And now I leave the word to Waters for the discussion panel and for the questions. And thank you so much for all the presentation. Waters?
Thank you. I hope that all of you enjoyed it as I did. We have still 3 people presenters present, so we will focus on those 3. If you have other questions for Charles or for the one on digital, on the Alberta one, sorry, don't hesitate to send an email to the organization with your question, or directly to the people if you have been able to note the email address, and to contact them directly for all your questions. So let's first do some questions for Peter. Peter, the first question out of the public is if you also have been able to do CPT on site.
On that side, no, we did not do CPT. We used electrical conductivity to map differences in soil structure. And I noticed there was a second part of that question. How does that work? Yeah, it's the electrical conductivity is related to the grain size. The smaller the particles are, the higher electrical conductivity signal will be. So it's not as CPT a more absolute way of identifying or describing soils, but it's more seeing differences in soils, and lower electrical conductivity signals mean in general more sandy soils and higher permeability, and the higher electrical conductivity signals give you an indication of a more finer textured soil, more clay.
I know that using other tools like MIP, it's most of the time, even not always, I would say, it's always combined with CPT. Is it possible to have your probe in a train like it is in the MIP train, including CPT, MIP, and so on?
Yeah, I think GeoProbe also has a OIP with CPT. So we do not service it at the moment, but it might be, if there is a lot of interest to do project in that way, we also can service it in that way.
Okay.
But it is also, you can also combine with a hydraulic profiling tool, and that's more an alternative to the CPT, where you measure the permeability of the soil by injecting a constant flow of water, and you measure the pressure you need to inject this water constant flow. So a low permeability soil, you need a high pressure to inject this water. So you really log the permeability of the soil during the probing with, for instance, the OIP or the MIP probe.
Yeah. And then a second question, also a really interesting one, linked to statistics, I would say, is if you have been able to do several measurements also at small distances to see the horizontal variability. So if you would do two soundings at 1 or 2 meters from each other, do you expect that you will have similar results, or would you expect that that wouldn't be the case?
I expect similar results, but not the same. I think there will be differences. I've seen this type of tools used in duplicates on other projects on other sites, and there is differences to be expected. But I think the differences will be less than when you try to compare soil samples of this so close to each other, because you have so much more data points that you. I see the product in a very fine fingered way that is dispersing into the soil. When you take a soil sample, yeah, you can hit it or you can miss it. You always need to take a sample of your soil core that is sent to the lab. So I think in soil samples, differences can be rather big. With these kind of techniques, you have a much denser data, a much higher data density. So I think the differences might be leveled out a bit. But expecting the same profile, no, there will also be some variability, and that's the difficulty of this type of contaminants, I think.
Okay. Then there was a question if it would work in the saturated zone as well. I believe so. No
yes,
intent,
yes. At this site, I think the groundwater level was about 5 meters below ground level. We used it in the Netherlands on a site to 35 meters below ground level with the groundwater level at just 2 meters. So
yeah,
it also works in saturated.
Sorry. And a question from my side on top of that. If you compare it with other techniques to measure pure products, I'm thinking of LIF and so on, laser-induced fluorescence. Do you see difference? Do you see similarities? Do you believe that this probe is more accurate, or?
It's the same. The principle is the same. It differs a little bit in details. With the LIF system, you get a full spectrum of the colors. Of course, you use the different filters. Here you see the images, so you have maybe comparable information, but less accurate, I think. But another difference is that you really see the pictures. So with what we noticed in a project where we applied it to heavy tar product, sometimes these type of products can really stick to a probe. And because you have each 1.5 centimeter, you have the image. You can see these contours of the product that is sticking to the screen of the. So you know when this is happening.
So you can see that you don't see anything.
You can see that what you see is sticking product. You see fluorescence and you have high signals, but you know that these high signals are falsified because it's the product that you're dragging down. And with the LIF system, you cannot see this picture. You just see the spectroscope output.
Yeah, and you have showed as well results vertically, and then you saw sometimes really some small peaks at much deeper than the former large peaks. Are you sure that this is still a pure product, or could it also be? Could you have interference with, for instance, organic matter in the soil or something like that?
This type of measurements. This type of measurements can be interfered by organic matter, and then again, since you see the fluorescent image, you can really recognize if there is organic matter, if there are maybe some material. You can see the form, so you can probably work around or identify it when this is a false positive.
Yeah, so really a lot of human interaction is still needed to come up to the right interpretation.
Yeah, but that's what's happening when you apply it in the field. You're constantly looking at each image that's coming by. So yeah.
Okay, thank you very much. Then the next very interesting presentation was on tritium measurements. I don't see any questions from the public when I'm right. Nevertheless, from my side, I'm always happy to see that even negative moments like this tritium release in the atmosphere, which was in fact a disaster, led to a good moment for us as scientists to see that or to be able to use it in a positive way. I fully agree with you. It's really interesting to see that you can use it to understand much better your aquifer system. What is typical cost of a consultant? What is the cost of such a campaign? If you look at now, you have a clear view on this system, on this aquifer system. What does the total cost? What does the total project cost? Is it feasible to do it everywhere, or is it something that we can only do in exceptional circumstances?
So it depends. It depends on what kind of samples, because if you want to better characterize an aquifer, it's better to have different kind of samples, not only 1 or 2 or 3. And it depends on how the aquifer is, because if you have an aquifer multi-layer, you can collect the samples in the different depth. So the monitoring, the campaign depend of the geology of the aquifers, but and the cost of analysis depends if you need enrichment or not. Generally, yes, because if you don't need enrichment, it's very dangerous. But yes, it depends of a lot of yes, question and time.
Yeah, and what is the cost of one analysis? Could you give an indication on that one?
Yeah, so maybe an 100 euro.
Okay. Yeah.
Yes, if you have a lot of analysis, is not 100 for a lot. The cost is reduced.
Yeah, but it could also be a way to check if I fully agree with you, a multiple layer aquifer system to check if your well is not creating a cross contamination.
Yes.
That could also be an application of the technology. Okay.
Yes.
In the meantime, Marco asked in the chat as well, what are the new developments of this technique? So how do you see the future? The question of Marco, how do you see, what are the next developments of this technique? How do you see the future developments? Chiara, that's still a question for you. I don't know if you... Really at the last question, yeah.
Yes, that's next development. The next development is to use this technique more, because now this technique is not used to characterize groundwater, not only for the cost, but because people or other research center or university don't know that, for example, us can do this analysis. And maybe they don't know that this type of analysis and this type of methodology could be used to characterize groundwater, especially to characterize groundwater related to anthropogenic pollution, because this is the best information for this methodology. Generally, they use this methodology to date the aquifer, if they have young water, old water, but not especially for the pollution of the groundwater. But it is more important, this.
Okay. So once again, thank you very much for the very interesting presentation. We move to questions on the last one, that the last person that's still alive, Zach. There have been already a lot of chats going on that someone is wanting to use it in Iceland, and that's possible. That's the answer on the question, if it's a global system. So it seems to be working everywhere. That's the right understanding.
That's correct. Yeah, you can zoom into any location on Earth. The amount of data, pre-processed big data that is available varies based on the site or the geographic location. We have the most pre-processed data available in the United States, and even more detailed data available in Michigan. But we're constantly expanding our data coverage across the globe and trying to improve the data coverage and resolution and quality. But there are lots of options for users to add their own data, their own raster files, their own observation data, their own data about the geologic framework, etc. We're also focused primarily on groundwater, but we're also expanding into surface water modeling for watershed processes and channel flows, reservoirs, etc. So right now it's groundwater. The data is mostly limited to the United States, but we're improving and expanding continuously.
Okay. For me, in modeling, one of the main topics is that due to the fact that it always shines brightly and that it looks marvelous, that people blindly believe what they see and don't take into account the uncertainty. You are fully available on basic data, the level of detail of your basic data. Is there a way to include this uncertainty in your modeling, that you could say, well, this is the map with the prediction of the concentrations. In some zones we are more certain than in other zones. Could you include this uncertainty visualization as well in your model?
Yes, you can. Yeah, so you can map out the variability or the uncertainty of the flow or the concentration of some sort of dissolved chemical. And so you can run many different models for slightly different representations of the subsurface following some sort of statistical distribution that you garner from your field data. So you collect some field data, or you may have no data available at all, but you can represent the subsurface using those data in some sort of statistical framework. And then you can visualize how the mean concentration at a particular location changes over time, how the variability of concentration changes across space based on the results from different realizations. So yes, you can analyze that and visualize it using the software.
But you still have to do it yourself by modeling different situations, and not that you give a kind of a warning, be careful, you don't have enough basic data to get a reliable result. Something like that is not included yet.
Yeah, so we set up the software such that the very first model that you would build by using the default parameters is just a very simple 2D model. And you're correct that as you try to model more details, it requires more expertise and more critical thinking. And so obviously it's a powerful visualization software, but it still requires that the modeler
knows what he's doing.
Okay. But we do offer on the website a lot of curriculum educational materials. And so people can learn about groundwater modeling as they use the software. We actually have homework assignments and projects. So we try to recognize that that's a great point, that you need to understand the process and the conceptualization before you can fully trust your model or evaluate your model. So we do have some resources to aid with that. Okay,
thank you very much. There's still a last question from Marco. Marco?
Yes, Wouter, thank you. Zach, sorry, you showed that your system is able to predict the evolution of contamination and in groundwater. Could it be used on the contrary to understand where are the source of contamination, or also where I don't know, a contamination is installed, so it's a secondary source that is releasing?
Yeah, that's a great question or comment. You can certainly do that where you know you have contamination at some location and you're trying to figure out where it came from. So our software allows you to backward trace contamination. And so you can trace backward the contamination to try to find out what the source is. You could also trace backward from some sort of groundwater receptor like a water supply well or a wetland. And so you can map out where is the groundwater coming from that supplies that well or that wetland, etc., and you can protect that. So that's, wellhead protection areas is what we sometimes call those. So yes, you can trace backwards, and that's a common application of the software.
Okay, I believe it's time to. We have had all the questions. If there are no.
Wouter, if I may have also one question for each Peter and Chiara.
Yeah.
I think we have still 5 minutes to the end. Peter, it's let's say more or less a commercial question. I know that it's costly, this kind of analysis. how do you convince the clients that is better to have a good conceptual site model instead of going to the remediation blind?
Yeah, I hope my presentation indicated already quite some answers on that. As what I've seen in all the site investigations that we were involved, if you go into blind, we always find some product at places where it's not expected. So it's really important to reduce uncertainties in site evaluations and add some more data, remove all these data gaps, because the products are dispersing in such a complex way. When you just use monitoring wells, yeah, the chances that you are at the wrong location sampling are so high. I think for DNAPL products, you really need this kind of investigation tools to make a sound conceptual site model.
On top of that, and Peter is not working in the same company as I do, but what I always tell clients is that if you compare the level of detail, and even imagine that you have only 5 centimeters an analysis, an indicative analysis, if you want to do something similar with soil samples, you need 20 samples per meter, so you have 400 samples, 400 analysis in one place, and the price of 400 analysis is much more than the price of one sounding. So that's a comparison you have to make, and sometimes you really have to convince people. Marco, you know as well that I've been in favor as well of promoting it to Italian authorities, but it's in fact absolutely necessary to, if there's a risk of DNAPL and you don't do this kind of soundings, then you are really working completely blindly, and that's what we should avoid. But we all have the same opinion, I'm afraid. I believe.
The question for Chiara is for the application of this technique could be applied also in developing countries. I'm skeptical because I know that you just told to Wouter that 100 euro for each analysis. No, but because I'm telling this because you know, in developing countries, water could be a scarce resource. So could be a good way to understand if their groundwater is recharging and in which way.
Yes. So the cost of the analysis is due to the enrichment, to the distillation and the enrichment procedure that during 2 weeks only the preparation of the samples. But if we have to analyze, for example, in place in which the water recharge is more important, for example, in a project, we can find some way to do the analysis without charge. So yes, the way we can find a lot of different ways. The cost is, for example, for private people, for private, for example, for ARPA or for private industry and so on.
Thank you.
Okay.
Thank you. Then I would like to close, and for me, 2 main messages. Thank you for joining. I hope you appreciate it. Feedback is always welcome, don't hesitate. And secondly, the next session will be in 1 hour. So for the early birds in US and Canada, you can run to your coffee machine and see that you are fully awake in 1 hour again. For the other side of the globe, I hope you can enjoy some lunch, some dinner, and then come back. And for the Europeans, enjoy your lunch as well, and see you back in 1 hour on the topic circular economy. And I believe it will be quite interesting as well again. Thank you very much, and see you soon. Ciao.
Thank you all.
Bye.
Bye.
You will be on high resolution characterization next one, not in circular economy, just this.
Okay.
Okay.
Thank you very much.
Thank
Bye
you.
bye.
Bye.